Hey guys, it's Edbert. So I thought I'd do something a little different and actually run through an example of how I actually study these patterns. Consider this as an addendum to my previous video. What I'm going to do is I'm going to do this completely raw with my old grokking account. I'm going to be going over to a single pattern. I'm going to be trying to do a problem from that pattern, and then I'll be applying that to a previous data structure or pattern that is similar. By doing this, I'll be trying to apply that pattern incorrectly and seeing what I can learn from this. But before I begin, if you could tap that like button for me and turn it blue, that would really help me out. It lets me know that you appreciate what I'm doing here and that you like these videos. So with that, welcome to the coding interview. You suck. So I'm here logged into my grokking account, and the last time that I was in my account was probably about 8 months ago when I was first studying for my interviews. And as you can see, I really wasn't doing that many coding interview problems. In fact, I only got through like maybe half of them before I felt sufficiently comfortable with most of the patterns. So if I look here, the sliding windows, I did a sufficient amount of them. I didn't do the challenge problems. The 2-pointer ones did half of them. Fast and slow pointers, definitely a whole lot more, almost all of them except for the challenge problems. The merge intervals, this one I definitely struggled with if I had to do almost all the problems. Cycle sort, this one I didn't really do too many, only because I felt this was something that wasn't going to come up in interviews that much. In-place reversal of a linked list. I felt, at the time, I felt this was pretty easy for me. Breadth first search and depth first search was something that I felt very comfortable as well, so I didn't really do it. In fact, depth first search I didn't do at all. Same with 2 heaps. I didn't see a scenario when 2 heaps would actually come up as an optimal solution. Subsets, definitely something I would recommend you guys do. I'd spend some time on it too. Modified binary search. Bitwise XOR, not something I would see very often. I don't think it would be ever asked. Top K elements, definitely worth practicing. I think this one was with heaps as well. K-way merge, probably K-way heaps, if I had to guess. I don't really remember these patterns anymore. And so topological sort, dynamic programming, I didn't even do any topological sort. So what's the point here? The point I'm trying to make here is that you really don't need to do too many of these problems in order to start feeling comfortable with the patterns. But the goal here that we're trying to do is really just understand the pattern. So I thought I'd spend today to try and show you how I would do something like this. So the only question left is really to figure out what pattern I'm going to try. Oh, actually, let's do depth first search and breadth first search, because I think it's very easy to not really know when or where to use it. And they're similar enough that I think it might warrant actually making a distinction between the two. So let's start with depth first search. Given a binary tree, find path S. Cool. Problem statement. You want to find a path from root to node. Okay. So how might you go about doing a depth first search? You would probably just do it recursively if I had to say so. So before I even touch the keyboard, what I'm going to do is write it out here. So I'm going to do as path root sum. So then here will be my. So that was a little messy. So what I'm going to do here is I'm just going to keep rewriting this over and over and over again until I can basically do this off the top of my head without really thinking. So I'm going to speed this up for you, and I'll see you in a little bit. Okay, I'm back. So, looks like I did it about like 12 times. At the end, my function call definitely got a lot cleaner. I removed the parameters because I just didn't see the point in doing it. So for comparison, the very first time I wrote it, it looked like this, where I was passing in the sum. I don't want to draw on the hidden layer. I was just passing in the sum for no reason, and I was returning a value. here, which is fine, but as I progressed onwards, eventually I think it got probably around layer 9 or 10. I got pretty sloppy and they just said, fuck it, I'll just remove it because it gives me no added value. And so around layer 10, 11, and 12, and the 12th layer was the last one I did, where I just took out all the parameters and return values. But I can always add them back in because I know that I can just add the return value here. I can always add the return value back here, and then do my value evaluations. If I had like some kind of value here, then I had V1, V2, and I can always do my evaluations like this. So at least I have the base skeleton, which is exactly what I was hoping to get. And I think I've written it off the top of my head pretty much a few times that I feel pretty good about it. If it turns out that I didn't, then I'll go back and do it over and over again. But essentially, this is the way I start off any pattern, that I just get the base case down. So, moving on, let's actually do this first problem here. So, what is it trying to ask? Given a binary tree and a number s, find if the tree has a path from root to leaf such that the sum of all node values of that path equals to s. So it's just a true-false statement. Okay. So it's just checking it to see if a path exists. So, it's very standard. So, what I'm thinking about doing is that, let's say I have a value here, A, then here, B, C subtrees, that I have a sum here, right? Let's call this S. So, I just need to find out if there is a path of S minus A in the subtree. So if that's true, so if this is true, then return true. Seems simple enough, because S minus A plus A is going to equal to S, which is the value we're looking for. So passed in value here will be S. The passed in value here should be S minus A. So instead of, and the return type will be true or false. Cool. Cool. Okay, so we defined our parameters. Now what's our base case? Our base case is going to be if it's null, so the first one is null, then we want to make sure that we just return true, because we just have null be the value. But essentially what we want, actually no, I take that back, because what happens if null, we get back a value, we still have like some value remaining and that we haven't resolved yet. So this value should actually be false. So, because we are looking for a value here, and we have found no value that matches that, so we're fine. All right, the second one is if we have a single node, right? S, or let's call this T, and then null null. So the idea here is that we pass in some value S, and then we try to match it to T. If there is no, then we should return false if the S does not equal T. But we're gonna pass in S minus T into here. T into here. That's fine. And then, which means that because there's a value here, that this must be, well, this will hit our base case here, and return false. Now, we want to also, this also brings up a point of, well, what happens if it's greater than 0, less than 0, or equal to 0? 0, 0, 0. So, if the value is less than 0, then we return false, because no more numbers that we go down is going to give us that sum, unless we assume that there's possibly some negative numbers in here. And it looks like based on the case that they gave us here, it's not the path. It's not. So, although I feel like we would want to, this is probably a good clarifying question to ask. Are there positive and negative numbers? Because this does change whether or not we need to handle it. So for now, because I think it's supposed to work in a general sense, we'll just assume that it gets handled by the base case here. So which means that if we ever hit this terminus, we should always return false. That means that the only other case that we have to handle is true. So which means that if s equals to t, return true. So here, then 3, which is base case 3 is actually up here, which is we have 1 or 2 values. And we only need one of these values to return true for us to be true. Return if left or L or R is true. Cool. So let's actually write this up. I always do this pencil and paper before I even touch the keyboard. So let's write this up. I'll do pseudocode first, and then I'll touch the keyboard. So based on what I just said, has path, and then we have root sum, and so the base case. So our base cases here will be if root null, false, and so otherwise if sum equals to value, return true. Otherwise return path of root dot left sum minus val, or path of root dot right sum minus val. So this is my skeleton. As you can see, this pretty much mirrors whatever I was with the base pattern that I was talking about here. So here we have our base cases. If root is null, this might look familiar to you. Our values are here, booleans here, and now these are our recursive. So that might look familiar to you too, except I just instead of writing these separately, I just compacted them into one line. And going back to what I did up here, does it match what I want? The first case, if it's null, then I return null, which is true. Cool. Second one is if the value that gets passed in to t does not equal. Well, we just agreed that we would let null handle it just to handle the case of positive or negative numbers. So the only case that we handle is if it's equal to 0, which means s minus t is equal to 0. So yeah. So this is if the sum is equal to value. Cool. We'll match that. And then here we've handled our left or right cases. Cool. Let's code this up. So let's talk about backtesting this against some other patterns that we might have encountered, like the breadth first search here. Now this is a fairly trivial problem. After all, we can illustrate what happens if we end up doing depth first search versus breadth first search. Breadth first search evaluates things on a level by level basis, but depth first search just evaluates on a root to the children basis first. That's pretty self-explanatory, but let's see what happens if I try applying it to one of the challenge problems. So, connect all level order siblings. Given a binary tree, connect each node with its level order successor. The last node of each level should point to the first node of the next level. Cool. So, as I said before, now that let's assume that I did the depth first search first, I mastered it, and now I want to do my breadth first search and test these problems against what I previously figured out. So, what happens if I take this problem? I know I'm going to do this with a breadth first search. That's kind of already given away with the pattern. But what I want to do isn't that. What I want to do is try to backtest this against my depth first search. Is there a way that I can do this problem with a depth first search? So what happens if I try to do 1, 2, 3, 4, 5, 6, 7? Now, again, it's very obvious once we do a breadth first search, but what we're trying to do is actually do this with a depth first search. So this will kind of depend on your traversals. So let's assume that is an in-order traversal. So we'll do 1, 2, 4. So 4, 2, 5, 1, 6, 6, 3, 7. And as you can see here, if I were to segment this, you can see that this covers left, visit, right as well. So recursively, it comes back to this. So how do I get from this all the way to my desired result of 1, 2, 3, 4, 5, 6, 7, 8, 9? So let me erase this and rewrite it cleanly for you guys. So how do I get from here to 1, 2, 3, 4, 5, 6, 7? So how do I get there? Well, there are different types of in-order traversals. I can do pre-order or post-order as well. So if I remember my pre-order traversal right, it should be VLR. So for the pre-order. And then my post-order should be, I think it's LRV, right? Knowing that, how do I get to this result from these two? This looks like the closest thing that we can get. The only thing is that these 3 and 4 are swapped around. So I'm gonna try chewing on this problem for a bit. I'm gonna fast forward it for you guys, and I'll let you know what my findings are. Now, this may or may not work. I actually do not know. So I'll speed through this, and I'll see you guys in a little bit. Okay, so I might have figured something out. So the idea here would be to keep a global list of lists, essentially. And so you would have a list for at height of 1, height of 2, height of 3, And at each one of these lists, what you would do is as you go further down the recursion, you start at, let's just start at 0, 1, 2. Just for the sake of just to keep things interesting, keep the indices. So height of 1, height of 2. You would just keep a list here. So here you would, as you visit it, you go 1. Here at height 1, you would have 2. Height 2, you would have 4, and then 5 as you visited it, and then you go back up, and following back the traversal, you would have 3, and then here you would append 6 and 7. So this does give us the answer that we want. It transforms into this shape, and then afterwards we can just append list after list after list. But let's actually see what this looks like in code, in pseudocode. So I do have the idea here. Now let's what happens in the base cases. So my base cases are going to be 1, when the node I arrive at is null. So actually, no, I need to figure. I know I'm going to be passing in the I'm going to be passing in the, what's it called, the height. So input is going to be h, and then it's going to be a void function because I'm keeping a global list. So that means that the first case is if I'm entering null with some kind of h value. Well, what does this mean? This means that I don't want to add anything because according to this, at least example number 2 over here, that it just doesn't get added. So then we just return no op. 2. Second one is if I come up with a value with null and null. So then this will just get added to list at h. Cool. And then the third one, we have A, B, C. So then add to list, and then just go into children with h plus 1. Cool. So I think this pretty much works. We covered our bases. And then after that, after we've iterated through the entire tree structure, we're going to iterate through our list of lists and then append them one after the other. So Let's write the pseudocode for this. So my function here is just going to be a iterate. So let's call it main, and then this is just gonna be our normal entry point, and we have a node here, right? And so the first step is the iteration. Second step is the assembly. So let's do iteration. The iteration here will be, as I mentioned before, root. So DFS root height. So if root equals to null, then what we're going to do is, based on the design I just proposed, we're going to turn a no off, so just return. So now if the root is just a leaf, then we just add our list at h. So then our list of lists, we'll just call it the height list. List. I should come up with a better variable name for this. Dot get at h dot add will be root. Of course, with the possibility of this is null. So we'll do get or default. We'll just transform this into get or default. So that way we just guarantee ourselves that we have a list. So that way we're not gonna get a no pointer exception here. And then we got to add that back in. So then here we'll just draw a little arrow, list of lists dot set at list of list dot at h comma list, and then we should be able to remove it beforehand as well. So remove if exist from L. So actually it makes more sense just to remove it and it check if it's null. So let's actually erase this. Exist from null. Remove if exists from list of list. If null, I'll create, and then we'll just do list of list add and then list of list set. So that way we know that we're gonna have a list at that point. Cool. So now let's go to the other case where I have two children. So I'm gonna just iterate into those children. Cool. So then DFS to root dot left, DFS root dot right, and I said I was gonna add h plus 1 to it. Okay, sounds reasonable. And then for the assembly step, it's a pretty simple traversal through the entire list. So traverse and append all lists together. So I think this actually works. So let's actually go ahead and prove it with the code here. Okay, so we're back, guys. I did solve it, but there were a lot of pain points in doing this approach, and I'm going to tell you what they were and how I'm going to use these in order to prevent myself from making this future mistake. So, first and foremost, the thing that actually got me into trouble was actually this condition here. Well, is this condition of L.L.size is this condition right here. This condition got me into some trouble because while it was clear that the h is equal to the index of retrieval, in my mind, it was also a point of I didn't really understand how the order of traversal worked. So, to clarify what I mean, this was my initial proposal. My intention was to retrieve the list at h, where h was the height. However, I don't know what I was thinking, because if h is greater than the total number of lists, then we will have an out-of-bounds exception. And while we might attribute this to just rushing and being sloppy, there is also another lesson here. The other lesson is that we should try to avoid referencing data structures outside of the recursion. So, this is the first mistake.
The second mistake I made was rushing into the assembly step. That is, because I was so confident in how I envisioned the algorithm, I overlooked how to actually do it. This led to a bug in the code where I would be post-pending lists out of bounds. In the future, I'll be a lot slower and not assume too many things without proving it. This is a pretty common problem and, well, looks like I made that mistake.
Now, what did I learn about the pattern? The pattern is that if I need levels first, do a breadth first search. If I want a path first, then I want depth first search. And so out of this session where I did 2 problems, one easy, one hard, I learned 2 different things. First one, avoid having to do these flags. If you do these flags while iterating or through recursion or referencing some external structure outside of recursion, that's going to get you into trouble. And the second one is try not to flag like this when you're doing loops, just because it's just way too easy to get caught up.
Okay, so we learned a few things today. I wrote a pattern over and over and over again until I could do it from memory. Second, I tried it out on an easy problem just to demonstrate how I would have tried to master the pattern. In a real study session, I would have tried this on multiple patterns until I felt sufficiently comfortable to using that pattern. Then, I backtested the depth first search pattern with breadth first search and see what would happen if I tried doing that. The result was I learned 2 things. The first one is to avoid having to do complicated iterations with flags and external data structures. The reason why is because maintaining a global record of something that is readable and can be modified at all stages of the recursion leads to a lot of messy code and potential issues. Second, while it might seem obvious in hindsight, you would use a breadth first search to traverse by levels and depth first search if you want to traverse through the path that you take. If I have to maintain a global record of my past paths, then I know that I should not be using depth first search, but instead should be using breadth first search. As a follow-up to this, I would try the exact same problem that I did for depth first search with a breadth first search and see what happens. I'll leave that as an exercise to you viewers, but suffice to say that you can uncover a lot more mistakes and a lot more ways to recover from those mistakes by simply just trying to misapply patterns and data structures. I admit that I probably rushed into it a little hastily, and this is something I could definitely improve on, so I'm only human, and I make these same mistakes as well. What's important is that I can learn from it. As you can see, within this 1 hour, I learned a lot. Now, imagine doing that for just 100 hours. So, with that, let me know what you think in the comments below. If you want me to do another pattern, or you think I might have missed something, please let me know. If you like this video, please like and subscribe, and I'll see you all in the next one.